Right, okay, everybody. Well, look, let me say thank you for joining us here at, I've got a little timer running there to keep me on track. So, right, yeah, so this is an initiative by Makespace, or what could we do online for people during the lockdown. And myself as an electronics engineer, that's what I do for a living, design widgets. Thought, you know, we could do like a hands-on, you know, it's not a derivation of any electronics. It's really just, you know, simple things that you can do in your circuits. And I've aimed it primarily at people who've got like a GCSE sort of level knowledge of maybe maths and physics. And there's a little bit going all the way to those to like myself, who are the professional engineers doing now for a living. So you can add a few tips and things in there. So bear with us if it's a little bit too complicated and or a bit too simple. So hopefully I'm trying to do just a little bit for everybody is the intention here. And so the first one, which I thought we'd play with, would be on power supplies. And so I thought we could have a look at different types of power supplies, batteries, how to protect your circuits with just different ideas. And then we can have a look at some linear voltage regulators and some switch mode regulators and inverters. So a little bit of a flavor of everything. Probably all different levels, and probably for maybe half an hour, and then we can have a chat if anyone's got any questions or wants to run over anything again. So everything that we're doing here I've done as a download. So if you look on the chats, you'll see there's a Dropbox link, so it might be difficult to see some of the stuff here under the camera, but it's all available already for you to download at any time. Right, okay, so I'm going to switch to a different camera for us. Don't need to press leave. So I've got set up here. Here we go. Share. Right, so I've set up for us here a overhead camera for us today. And I thought the first thing maybe we could have a look at for designing electronics would be the all-important power supply. So I'm going to do a little bit of juggling here with the camera, because I think I can get, there we go. Right, so I think if you're going to use a power supply, something like this, which is adjustable, but I think the most important thing to consider with power supplies is one that's got a variable current limit setting on it. So if you do have run too much current, then you're not going to go and break your circuit. So what we're going to be playing with, we're going to want to know just shy of an amp for stuff we're going to play with. And if you're going to have a power supply, just spend your money and get something decent, I would say. 60 to 150 pounds is really what I think you should be spending. So beyond that, I'm just going to try and unjuggle now. So that's the last time we're going to play acrobats with that camera. There we go. Well, got out of that one quite quickly, didn't I? Right, there we go. Right, there we go. We're back. Won't be doing that again this evening. Right, so I think the other thing, if you haven't got a power supply, of course, is batteries for your electronics. And what I've got here, this here is a graph of if using alkaline batteries. What you've got to be careful with the electronics is the fact that they have this rapid drop-off of voltage over time, depending on how much current you're drawing. So you can see if you're drawing a lot of current, this is typically like an AA battery. It's the sort of things you put in your Sony Walkman. Remember those? And so if you're drawing a lot of current, your voltage is going to drop off quite quickly. So you need to consider that in your power supply design. Or if you're using lithium, which I've got here as well, lithium is an alternative where the voltage will be nice and stable for your electronics. But the issue with lithium, of course, is they are very temperature dependent. So below 5 degrees, they do tend to pack up, and above 65 degrees, they do tend to pack up. And of course, in your electronics, if you're trying to monitor the voltage level, whilst, you know, in an alkaline battery, you can probably quite easily measure the voltage to work out when it's dead. Unfortunately, with lithium, they tend to hold their own and then just suddenly fall off a cliff. So monitoring lithium batteries is a lot harder than alkaline. The other thing, a little anecdote, years ago, I was trekking through the Himalaya and my camera stopped working. And the guide was with, this is 2001, he said that people bring their fancy cameras to the Himalaya all the time, which is quite high, and they always stop working. And it's because lithium batteries, which obviously lithium ion is rechargeable, they just seem to pack up when they're at low temperature. So there's quite a lot to think about there with, well, do I use alkaline? Do I use lithium? What are the temperature considerations? How am I going to monitor the voltage or the current flow? There's quite a lot to it, really, in how do we choose the right battery. Right, the next thing on here is how do we protect our circuit from damage? So I have made for us, I appreciate this is a little bit tricky to see on your screen, but this is all available for download. I have made for us a little circuit board here, so we can, there, hopefully you can see all that. There we go. So when I'm designing electronics, this is the input power here. We'll plug this in, I think. I think I'll that one first. So when I'm designing electronics, first thing I always tend to put in here, oh, I'm going to just turn that off there. There we go. First thing I tend to put in here is obviously this is the input, is some Esd protection on your electronics. These are just look like tiny resistors. I mean, you know, it's that tiny thing just there. You know, you'd lose it under your fingernail. And I then always put my voltage through a common mode choke. That's just to take some any interference on the power supply, just take any noise out. And then I thought the first one we'd look at would be here, which is this is a Polyfuse. I think you might find a Polyfuse on the Raspberry Pi. But we can do a voltage with this, test with this, so we can turn that on. So what I've done here, there we go. So I've got 3 little lights here, which is the power supply, and the bottom one, which is our Polyfuse. And this jumper here, we can actually adjust how much current we're flowing through it. Now, as you can see already, that says 3.72 volts. And we've already, I've got 5 volts in, 3.72 volts out. So I've already lost 1.3 volts, and I've lost that already across the Polyfuse. So if I take that out, it'll probably hopefully jump back up. There you go, to nearly 5 volts. So with Polyfuses, they look great. You know, and if the top one here, we'll put the high current through. Okay, suddenly the voltage drops to 1.6 and lower volts. So it's dropping all the time as this Polyfuse here heats up. So I think these Polyfuses are only great as a all or nothing. So if you've suddenly got a cataclysmic problem of current draw, then maybe a Polyfuse will save the day. But if you're using it just as a circuit protector, I just think there's too much of a voltage drop across them for them to be of any use. The other one we can use, which is my favorite, is to use a Mosfet transistor. This is a much nicer way of protecting your circuit. So no matter how much current, so now I've just moved my meter to the Mosfet side, which is this little tiny black box here. So they're quite tiny, which is this one here. And no matter how much current, if I put a high current through, I don't get the same voltage drop that I do with my Polyfuse. So it's a much better way to protect your circuit against reverse polarity, I would say. So if I swap my polarity round, I've just put the wrong voltage around the wrong way on the power supply, and it'll do a pretty good job of protecting the circuit. So I tend to not use polyfuses. I tend to use things like MOSFETs as one solution. The other solution for protecting from too much current, and this was an interesting experiment earlier. This one frightened me a little bit. Being live, anything can go wrong, and so I discovered earlier on one of my circuits, if you're powering from USB, which isn't such a bad idea, we can power this thing off with USB. Plug in here to USB. So this is 5 volts USB. Okay, there we go. That's close enough to 5 volts. This is a little tiny thermocouple on the end of a chopstick. And you can get these little tiny chips to protect against current. And so the idea is that if you have too much current flowing in, then it'll actually hopefully switch off. It's meant to have like a little tiny sort of electronic switch inside, which is another Mosfet transistor, which we were just looking at. So if it gets too much current, it can switch off. So what I found with them, I found this the other day actually. If I put my temperature probe on there, so that's currently not too bad at the moment. It's about ambient 19 degrees. If I put way too much current through it, okay, you can see the temperature starts to rocket sky high. Although it will start to fold back and protect the circuit, it does get outrageously hot. I mean, I don't know, we can put it on max. So I've discovered that some circuits, there we go, we can put it on max. I might hold then. There we go. So look, that's not good, is it? So I think I'm probably, the result of putting this show together for us, I've been using this to protect my circuits from too much current for a long time. And I think I'm going to have to go back and redesign all of this. So they're better than a Polyfuse. They've got the tiny MOSFET in there, so they should be able to switch off. But unfortunately, they seem to run away with temperature if you put too much, if you try and draw too much current. So they're meant to, because USB is limited to about 0.5 amp, USB 2, I think 0.5 amp. So the idea is that if you draw too much current, it should then protect your computer, but the expense seems to be how hot this thing gets when it's protecting your circuit. So I'll say I'm not entirely happy about that. The other simple way to protect your circuit, of course, is with a diode. That's an old favorite one. So we can unplug that and put a diode in. So I've got here, where's my favorite? There it is. So I have here for you, this is a very simple way to protect your circuit. We've got our power in here, still got my Esd protection, still got my common mode choke. But in this idea, I decided I'd just try putting a simple diode in. Problem with diodes, of course, is that they do tend to have a voltage drop. I'm not sure. So here I've got about 5 volts coming in, and this is just telling me what I'm losing across my diode there. So here I'm losing about 0.3 of a volt. So I think I chose a pretty good diode as that big chunky beast. So all diodes are different. The 1N4001, which is a standard diode for protection circuits, I think you'll find it's got probably about 0.7 volt drop across it. So you've still got a lot of current flowing through that. So we can, I think, hopefully, if I were to, our ambient temperature, take max off, about 18 degrees. So that's currently ambient. If I suddenly wind up the current flowing through it, look, it starts to warm up. That's because there's a voltage drop across it, and the current, which is power, and power always gets lost as heat. So if you're going to use a diode, then do a little bit of research and pick one that's got a very low, reasonably low voltage drop. So we're now losing about 0.7 of a volt. So if we had 5 volts in and our electronics were running, say, I know, 5 volt circuit, TTL. TTL's good down to 4.5 volts. I've now lost 0.7 of a volt, so I'm now in danger of my TTL digital electronics now no longer working. So the cheap and cheerful way of protecting your circuits isn't always the best way. Sometimes you've got to step it up a gear. Right, okay, so that covers protecting our electronics, which is nice. I put a few circuits on here to look at different power supply circuits. So what I've put together here for us on this very board is I've got 3 different regulator types. This is a small variable regulator, which is this one here, which we'll have a look at. I've then got this much bigger one here on a big heat sink, which we'll have a look at, and the bottom one is for switch mode, which we'll do that in just a second. So what we can do is, if we put that one on our regulator, so this one at the moment, I've still got 5 volts coming in. I've lost a little bit across my diode, but it's got now 3.3 volts from here. So if that was at 4.7 and that's at 3.3, I'm losing just a little bit of voltage, not too much, but it's all being lost as heat. And so with this small one, there you go, that's not too bad. That's tolerable, but I'm only drawing about 10 milliamps. If I increase the current to 100 milliamps flowing through this little tiny reg, it's still holding its own. That's pretty good. And if we put it up here, so my regulator voltage is starting to have a problem now. And you can see my temperature's going off to thermal oblivion. So that might not be for high current draw. These tiny regulators, although they say they're good for the current of a couple of amps, in reality, it doesn't look like it's the case at all, does it? So what we can do is we can swap to a completely different regulator, which is called Linear Reg 2. That's this big bruiser here. So I've taken a much larger regulator, which is more like this big one here. Just an input, an output, and ground. So it's pretty straightforward. And onto this one here, I've nailed an enormous heat sink. So fingers crossed with this one, we can hopefully see. Right, why is that saying 2.5 volts? Being live, anything can go wrong, of course. Oh, right, just cross there. Okay, that's fine. Right. So this is currently drawing this big one. Okay, so I'm currently now drawing about 100 milliamps on the meter, which you can't see, the power supply we had set up. Okay, so ambient about 18, yeah, and that's still holding its own. We'll now put this on the enormous current. So it's about 700 milliamps now flowing. And I would say it's warming up, but not nearly as much. So whilst these small regulators, they might say that they're good for the current, in reality, I think it's probably best to oversize and put a heatsink on. I also think maybe for if you're doing a battery circuit, so this regulator's measuring just about, say, 2.5 volts, and I've got a 5-volt input. That means I'm dumping half the energy from the battery as heat. Well, that's really not a good thing. That's fine for a bench top. I really wouldn't want to be doing that with a battery. So the question is, what do you do if you've got a battery? I would say if you've got a battery, the solution is really to use a switch mode power supply, which is, there's a number of ways of doing that. The easiest way to do is make a switch mode power supply. There we go, just move the jumpers around to set the board, makes life easy. So this tiny block here is a switch mode power supply, and I've got a few here. They do come in all sorts of shapes and sizes. This tiny Traco one, which is the one on the board here, the nice thing about it is if you do have a linear regulator, of an input, a 3-legged regulator like the one on here, this tiny regulator here, this is the switch mode, this is good for up to 24 volts. If you put that one on, it's a pin for pin drop-in replacement. So if you've got a problem, if you are using a linear reg, you can just desolder that one and just drop that one straight in its place and carry on as if nothing ever happened. So these are good ones. This one here is good for up to 24 volts. And it's 3.3 out. So, you know, if you think that was a linear regulator, 24 volts in, you'd be dumping over 20 volts times whatever current you'd be dropping as heat. So these would get outrageously hot and be inefficient. Whereas if you use a switch mode, even a simple one like this, off the shelf, Farnell or RS, be far more efficient. The downside I find with these switch modes, little modules, whilst they're great for development, they are shockingly expensive. So, you know, the tiny linear one here is probably a few tens of pence. These bigger ones here, you know, that might not be £1 or something. Of course, you've got a heatsink, which is another £1. Whereas these switch modes on here, I think this one is something like £5–6. This is probably over £10 because it can handle more current. So it's horses for courses, really. Yes, so I think I could tell you about switch modes. Yes, that's the other thing which I made a note of to share with you, is I find that if you're designing an analog circuit, I tend to not use a switch mode because it's just going to inject noise, electrical noise, because it's switching into your analog circuit. So for analog stuff, I do tend to stick with using linear regulators and try not to have too much of a voltage drop between the inputs and the output, so I can keep the current to an absolute minimum. And the other thing, of course, is if I'm designing an analog circuit and I want to power some op amps, where the analog voltage might be a function of the input voltage. If this voltage changes, you don't want your analog circuitry to change. So I tried to, you can get what's called low dropout regulators, where they've got a very small voltage drop, might only be about 0.3 of a volt, in which case they won't get too hot. If you're powering, like an op amp filter circuit, you probably won't be drawing more than, maybe 50 milliamps maximum. So it's not really going to get hot. And so most of the designs I've done recently with analog stuff, I've gone for that analog option. But for the digital stuff, which we'll have a look at in just a sec, I tend to use more the switch modes. What you can do for a switch mode is, and this circuit is there for you to download. So you can use this is a discrete version of a switch mode. And that circuit is this tiny one just here. And so you can see that the footprint area of that isn't enormously larger than this Traco one. There we go, is that a bit better? So you can see, so that circuit there is probably in here. That probably didn't cost you more than a couple of pounds to make. That cost probably £8. And this one here, which I've designed here, I've used this one here a lot for controlling like ARM chips, which are 3.3 volts. And this one here, I've never had a problem, and it's good for well over an amp, before it starts to have issues with temperature. But it can be a bit more fiddly to make. If you're making it by hand, it's definitely be a lot more fiddly. The other issue.
Can I ask you a question?
Yeah.
Just in stepping through these things, you were talking about protecting your circuit.
Yeah.
And from my limited knowledge, probably below GCSE, it seems like each of these things is protecting the circuit in a different way. So the MOSFET's not the same as the diode, is not the same as the switch mode, because the diode presumably is protecting against polarity, and the regulator might protect against voltage variances or whatever. Could you just talk briefly about what specific protection each of those things you mentioned provides, as well as just, you talked about the characteristics, but not the specific thing it's protecting against?
Right, yes, okay. So let's just pause that just for a moment. So we can just head back here to, so with the basic one with the diode, for example, your diodes are pretty good at protecting against reverse current, although they won't stop it completely, but they'll protect your circuit enough such that if you got your battery in the wrong way around, you're not going to get a sufficiently high current through your circuit to do some damage. It's cheap and cheerful. It's probably, a few pence, but the trade-off is you're going to have this voltage drop across it. So you might start to have problems with powering your electronics because you've lost too many volts across the diode. So the way to solve that particular problem of this voltage drop is to use a Mosfet transistor in a simple this configuration, where this is the gate here tied to ground, and so this won't have a voltage drop across it. So if you do get the polarity back to front, on the power, you plug in power supply or the battery's in the wrong way around, it'll stop the backflow of current. So it's all about really protecting your electronics downstream. I tend to use this one. I'll be honest, I never use a diode. I always go for the Mosfet transistor. It's more expensive, but I don't have a voltage drop, so my battery will probably last a bit longer. And the Polyfuse, there's always a voltage drop across it, which is an issue. And the more current you draw, the bigger the voltage drop. And so, if you've got a battery, you're just wasting all this as heat. And so I find the best one is the transistor is definitely the best one. And I did mention earlier as well.
Just to be clear, the polyfuse isn't protecting against polarity, it's protecting against overcurrent.
Overcurrent, yes. So it's current and polarity. Yes, absolutely. The other way to, rather than using a polyfuse, the other option is to use a chip, which I've got here. If I just unshare this screen a second and share with you a different screen, because I think it might be this one. Hopefully this is the right screen. Yeah, so this is the data sheet for the chip, the other way of protecting against too much current. So hopefully there's a mouse moving as well. So there's the inputs and the outputs, and usually if it measures too much current, it'll try and switch this off. So again, it's another MOSFET for protection against too much current. But why it goes off to thermal oblivion is another question. So it's only got 5 legs. It's a drawing here. Here we go. It's a nice drawing. So power supply input, load output, and if you draw too much current, it's meant to send it is a pull down flag. So you could have that to like an LED or something. It's an open drain, just why it's got a 10K pull up. So this might protect against too much current, but it seems to be at the expense of the device. I'll have a look at that, and maybe I'll have a 5-minute ditty on it next time and see if I can explain why was it getting so hot. But on the plus side, when you are within the current limitation, you're not seeing the voltage drop, which you do with a polyfuse. So I think possibly, if you're polyfuse, if you're looking for all or nothing, either a few milliamps or suddenly trying to prevent a couple of amps, maybe the polyfuse is the answer. But as I say, I'm just really not a fan of them.
Can I just ask, how is a polyfuse different from a standard fuse?
So a standard fuse, when you get too much current, it's a wire that will just heat up and melt. With a polyfuse, it's really just an enormous resistor. So it'll heat up. Let's go back to my circuit page. So a polyfuse, it'll heat up and it doesn't so much break, it just becomes an enormous resistor. And then when it cools, the resistance drops again to, back to maybe a few ohms. So it's almost like a self-resetting fuse. I think it's possible if you, can I zoom in here? All right, this might work. Right, maybe if I try refocusing my camera. Oh, look at that, that worked. Right, so yeah, it almost just looks like a resistor. So it's a surface mount. So obviously with a normal fuse, you'd have to pull the thing out and replace it, but with these, when they cool, they just remake. So they are just a few pence, but yeah, I'm not happy with them.
Got a bit of a question of my own, if that's okay, Stephen.
Yeah, anything.
Yeah, I'd put it in the chat, but you not spotted it. Very much at the start of this, you were talking about the tail-off characteristics of lithium batteries with temperature, ambient temperature. Now I've got a potential application here in high-altitude ballooning. That's basically sending sensor missions up to anything up to about sort of 100,000 feet, and obviously temperatures up there are on the slightly chilly side. What's the trade-off between is it a valid trade-off to use the battery pack's own energy through a thermal blanket to maintain its operating temperature range?
So I think what you're going to have to do, you're going to have to put some temperature sensing in there. When they start getting like to 5 degrees, they will start to pack up. And if you've got a commercial, lithium with its own built-in charger, very often those chargers themselves will detect low temperature of 5 degrees, no, less than 5, and just physically stop working.
Right, because I mean, what's in my mind is obviously you're chewing up some of the battery's own power to warm it up. I was thinking in terms of some kind of sort of thermocouple switched system, so obviously it doesn't activate until it's absolutely needed, and then only as long as it's needed. But even then, obviously you're burning some of the battery's power to keep the battery in operating temperature. And what I'm not clear about, and haven't been able to be clear about, is the trade-off between the battery the battery power loss for the heating versus the lower battery capacity if it was unheated.
Right, okay. I'm not entirely sure I'm going to answer this, or if I can. I honestly
It's a tricky one.
Yeah, I honestly think, to be honest with you, you're probably better off looking at lead acid batteries rather than lithium. Now, of course, the issue, with lead acid will go to a much lower temperature. It's not going to have the same, I didn't get around to talking about battery capacity, which is measured in milliamp hours. So I didn't mention that. So a lead acid battery has probably got much better capacity. Milliamp hours is how much, in theory, how much sort of current you can get out of it in an hour before it's dead. So a tiny a battery out of your Sony Walkman might be good for, it might say, something like this might say something like 2 amp hours. It doesn't mean you'll get 2 amps out of it for an hour and then it's dead, and it doesn't mean you'll get 20 amps out of it for 6 minutes. It'll probably be a lot less than that for a lot longer. Whereas with your lithium batteries, you've got much higher density, but the amount of current you can get out of it per unit time is probably be a lot lower. There's a huge amount of trade-off. With your lead acid, which might be the one you need to look at rather than lithium for high altitude and low temperature. With lead acid, of course, they do tend to roll off a little bit more like this, whereas your lithium is going to hold its own until it falls off a cliff.
Yeah, the problem with lead acid is the mass, basically.
Yeah.
You're looking at a very low all-up mass, probably a total payload of 1 kilo or less, which makes lead acids basically infeasible.
Yeah, you're absolutely right. Couldn't agree with you more. I've lead depends how long is the balloon up there for. Can you keep the temperature? Could you put one of those, like a thermo pack around it first? And I don't know, how long is it up there for?
Well, insulation, I think, is one answer. Because obviously
absolutely, definitely. I mean, the
far less energy to keep the temperature up then.
Yeah, I mean, the setup I'm looking at is you've got a sort of a typical sort of USB sort of device charger pack wrapped around with a thermal blanket and thermocouple wrapped around itself by several layers of, it's actually satellite type multi-layer insulation. So yeah, trying to make the most of what you got.
Yes, it's a company called SAFT, S-A-F-T. They do a huge range of batteries for different applications. They might be worth having a look at. S-A-F-T, SAFT.
Right, thanks.
So they do a lot of specialist batteries. I mean, in fact, the one I've got here, this one here is a SAFT battery. So some time ago, I was working on a fire protection circuit, and of course, so we had a chat with them, and in fact, this is actually one of the batteries they suggested.
Right, thanks.
So there are batteries which for specific applications and different chemistries. So probably if you drop me a note on, say, silicon cortex, I will return with the contact at SAFT. So that's who I probably recommend you talk to, and you'll then get it straight from the horse's mouth as to what's good and what's bad.
Thanks very much.
John, would
Hello?
it be possible to have a battery that's dedicated to heating duties? Even if it's just one battery, and then have it's heating itself and the other battery that's doing the main power. I'm just thinking so that you dissociate loss of heat from because you've expired your heating ability from then completely crashing the battery power for everything.
Yeah, I have considered that, and it's not an unreasonable thing. The only thing is that these battery packs, the ones I was looking at, are typically about 250 grams all up weight. By the time you've thrown two of them in, you've only got half a kilo left for your total payload weight. So all your sensors, your computing, and all the other gubbins. But it's certainly not out of the question. At the moment, it seems like the best energy stroke mass economy is coming out of a single power source, but it's definitely an option I've considered.
One other thing you might consider are the chemical hand warmers.
Yeah, that's what I was thinking. Trying to think.
Might be better power to weight.
Good idea.
That's what I was thinking. How long is it up there for?
Yeah, well, that's the thing. It's it's upper. Well, we probably want to be thinking in terms of the sort of the journey from about 30,000 feet up to 110k, and that period is not that huge a period of flight. The balloon basically bursts about over about 100k, and then it goes on a parachute descent. So the parachute descent is initially pretty brisk because there's no atmosphere or none worth a damn. You start to pick up an atmosphere around about 70k, and it starts to become significant around 30, 40, which is fortunate because otherwise jet planes wouldn't work.
Be stuck up there all night.
Of course,
if they stopped working.
Well, indeed, yeah. So it's really this. It depends so much on the meteorological profile that it's kind of hard to put a number to, but you probably assume you're about an hour in the danger zone.
An hour. Okay, that's not...
In that case, could you have a jettisonable power, heating source so that it'll give it a good warm up, and then for the last bit drop off on a separate parachute, leaving the payload on thermal inertia to go up higher with less mass?
It's an interesting idea. I'd hate for it to descend on its parachute through somebody's windscreen on the M1. So I suspect, purely in terms of liability, that may not be such a good idea. The overall payload will be in a polystyrene container with some refinements of my own. That basically means that it's got additional crush proofing, which also means impact protection. So which should reduce the risk of things like that. But
yes,
a small power supply.
You could do that for the jettisonable part as well.
Yes, it's just a question of. Also, the question is how to do the cutaway.
Yes, that's a bit more mass as well.
I know, and annoyingly, you can't use pyro cutaways anymore, which I would love to do, but you can't send up explosives into the atmosphere for some strange reason. That's
very odd. I will say I've just looked up all about heat packs, and the apparently common one, which is iron charcoal vermiculite, needs oxygen.
Yeah, I was going to say oxygen's going to be a consideration for those. They may stop working when they get high enough.
The other thing is, of course, you've got no control over the temperature, and what you don't want to do is start cooking everything. So yeah, I mean, it's the chemical method is a good one if it's possible to find something that is in quotes, a slow burn that isn't oxygen dependent and isn't pressure dependent? Because that's the other big question, is, and anything that is chemical based, you've got to be bearing in mind you're going up to somewhere where the air's thinner than the Martian atmosphere.
Have you looked at lithium iron phosphate batteries, which apparently work down to -20?
When I first started doing this project, which has been shelved for some time now, they weren't yet an option, but they are now. You're absolutely correct, and I need to look back into that. The only question is, how much power supply do I want to design, and how much do I want to just buy off the shelf?
Well, you know what, on that subject, yeah, there are a lot of cheap and cheerful off the shelf. You get what you pay for. Okay, as I was discussing earlier, you can get these tiny little ones here, but they will spoil the look of a £10 note without a doubt. But they're a lot more efficient. In fact, with switch modes, because power efficiency is, if you make your circuit power efficient, obviously you can get away with a smaller battery, and that's not to be sniffed at. But they become most efficient when you're designing them. They become most efficient at the point at which they're delivering their maximum current. So if you are using a switch mode, don't go for one which has got lots of headroom. So, although this one here might be good for probably 3 amps, as a get out of jail, because your analog ones, turns out to be a box of spanners, then great. But as you drop off the maximum current draw, they start to lose their efficiency. And then there comes a point where it's actually no better off than using something like a linear reg. So stacks of headroom in a switch mode is a really bad idea.
Thanks for that.
One other thing I've got here is inverters. So, obviously if you've got up in the balloon, you've clearly got scientific measuring payloads. Obviously, you've got a negative power supply. Possibly trying to find a circuit for it. There it is. So a negative. So this one here. So what I've designed here on the board. So this one here. Hope you can see that okay.
Yep. Can you explain what you mean by a negative power supply?
I know, it's a bit crazy. So it's a negative voltage. So it's relative to the ground. So the ground is your reference.
Ah, right.
So that's your reference. Say your 0 volts. It's like if you put your multimeter leads on the wrong way round. Then they seem to be, what's that negative voltage on a battery? If you get the leads wrong, it's at like -1.5. So if you're designing, so like with your payload, you've probably got some sensing electronics and some filters. You're going to probably need a negative voltage for your amplifier. And I think in 3 months' time, we'll be talking about op-amp design and negative voltages that they require. Although they can run on single voltage rail for sure. Sometimes you'll end up with a negative gain, in which case you're going to need something that can go negative voltage as well as positive. Now, 2 ways of doing it, of course. Now, you could get, your two batteries, put them in series, and the center is 0 volts, and the top end is +0.1, the bottom end is -1.5. But of course, you've now got twice the weight, so that's not necessarily a good thing, particularly if you had, so one of these I've got on my desk here, sort of thing you might put in your ghetto blaster, if anyone's still got one. So if you started adding, if you wanted minus, say, 3 volts and plus 3 volts, you're going to need 4 of these big bruisers. Well, that's going to start getting a little bit heavy. So the way around that problem is use what's called an inverter. And it is, honestly, it's just a chip. That's all it is. This is it here. So this will run off our USB. So this is the plus Hopefully that says plus 3.3-ish. It'll probably creep up. It gets its act together. It's not getting hot. There we go. So I've got plus 3.3 coming from this switch mode circuit, which is this one here. And you could make that for, probably about £1, which is certainly cheaper than £8. And of course, it can end up being lighter as well. We talk about it safe in grams. I'll story about that in a second. But then, of course, you might want to create a negative voltage. So rather than using a battery, you can actually, from the same positive voltage, this is the 3.3 in. So this is my 5 volts coming in, wherever it is here. Oh yeah, that's my input voltage, that's my output 3.3. And from my 3.3, I've then created minus 3.3. Hopefully if I stick that on there, fingers crossed, it says minus. And it says positive. Brilliant. This is live demos for you. Right, okay, let's have a look at that. I should say minus. But they're very easy to configure. Like a analog regulator, it's just 2 resistors is all you need. And on the download, I'm not sure how well you can see that. I can hold up to move the camera a bit down. You can probably see. There you go. There you go. So to create a negative voltage for, say, an op amp, there's always a multiplication here, and it's just a ratio of two resistors, which is these 2. So it's dead easy to create. So from the same single power rail, whether it be a battery or anything else, it's very easy to create a negative voltage.
I've got an application where I need more or less the opposite of that. I bought a combined volt and ammeter for my car. It's a rebuilt car, wired it in. It's got a big shunt resistor, which I put in the positive supply, and then realized that the whole ready-made voltammeter only works with the shunt resistor in the negative, which I can't really arrange. So what I'd like to be able to do is double the vehicle's voltage, and then run the voltmeter part of it between the 12 to 14 volts and a 24 to 28 volts that I fake up accurately.
Mm-hmm.
What sort of circuit would you suggest I could do that with?
Okay, so say again, so your input voltage is what?
So I'm trying to measure the voltage of a vehicle system, which tends to be between 12 and 15.
Yeah.
And it's a combined voltammeter unit with a big shunt resistor that you're meant to put in the negative side of the circuit, which I can't do. I've put it in the positive side, not realizing it had to go in the negative side. So what seems logical to me is to connect the negative side of the voltmeter sensing to the positive rail of the vehicle, connect the positive side of the sensing to some circuit which doubles the vehicle's voltage. So I get the same voltage between my nominal 12 volt rail and the measuring one as there is between 0 and the nominal 12 volt.
Can you draw this for us?
Yes, probably.
You draw it and hold it up to the screen for us?
Yes, I'll just have a go at that. So I've got...
That's quite hard to get our heads around. You have to turn your camera on there.
Yes. So...
Anyway, whilst he's drawing that, so in terms of testing electronics, that's really, oh, there we go. Right, hold it up for us.
So I can't, not getting feedback on what mine looks like. Let's just.
Okay, hold it a bit closer for us.
So that's how it's designed to be.
Right. Oh, okay.
However, sorry, no, that's what I've currently got wired in. What it assumes is that you've got the shunt resistor in the negative rail. down there, and that you're measuring across that resistor.
Yeah, okay.
However, I can't do that because that's not how vehicle negatives work. So what I'm just going to put this down and draw what I want to end up with. So now I've got the volt and ammeter connected across the shunt in the 12-volt side of the supply. And to be able to measure that 12-volt voltage, which is assuming that this is 0, not assuming that this is 12, I want something that will create a precise a precise 24 to 30 volts from the 12 to 15 volt rail, so that the difference across here will be measured.
Okay.
So I can measure the vehicle voltage.
Okay, so that voltage from VA, that's just like a voltage, well, that you can read on the meter to represent the.
But no, that's the meter unit itself, a little ready-made unit that has 2 lines of LED, one showing the current and one showing the voltage.
Yes. Yeah.
So it's the module's got 5 inputs on it. 2 of them you connect across the shunt resistor, 2 you connect to what you want to measure the voltage of, and the 3rd is to power the unit itself. Sorry, the 5th one is to power the unit itself.
Right. So what's the issue again? With you want to put it on the negative, do you?
No, it's designed to go on the negative. It's designed to have that shunt resistor on the negative, and then seems to be measuring the voltage on the assumption that that's 0 on one side of that resistor, and that the other voltage you're feeding in is the one you want to measure. So it's designed to have 2 connections into the negative rail with a big shunt resistor between them, and one to the positive. I can't put it in the negative rail.
This might be a bit specific for us to get drawn into at length at the moment.
Yes.
Yeah,
Okay.
it might be. It was
your mention of inverters led me on to it. Yeah. I
yeah,
that might be a way of doing it.
Yeah, it's like all these things, and I was going to wrap up with saying about power supplies. It's very often, in my experience, in engineering, left as an afterthought, and it really shouldn't be. It's really got to be in there right at the start of how am I going to power this circuit. Yeah, I mean, measuring, there's a thing. I mean, like with lithium, of course, how are you going to measure that voltage when the thing is great and then just falls off a cliff? Well, we didn't talk about, measuring lithium. You do what's called Coulomb counting, which is where you measure the current flow, and you make basically it's an estimate, a calculation on how much power is drawn, which is how your mobile phone works. It's just doing a rough calculation on whether it's zapped or not. Obviously, and measuring the current flow from lithium batteries, Coulomb counting, is a lot more power hungry than measuring off an alkaline, which alkaline battery, you could probably measure the voltage, I would say, with a few nanoamps if you designed it properly, whereas you'd never get away with that with the lithium system. So yeah, there's many considerations, and what I wanted to do in this first little sort of session was, not show any derivations. It's more about things which we can use, and there are a couple of books on power supplies. This is one which I use. I actually got it from a company called XP Power. I think it's the people who make these tiny regulators. So there's a ton of stuff in there. Oh, the other book I use, this is a coffee table book, is Horowitz and Hill. Every engineer should have this on their coffee table, in my view, even if you never read it.
Oh yeah.
Is that to keep the coffee table in one place?
Yes. There is a section here. I did crack it open and share chapter 9. There is a version, a whole section on voltage regulators. You know, they give all sorts of you know, lots of good stuff there. You know, to if you're suffering with insomnia, this will certainly cure you. Right. Well, look, it's coming up for an hour. Any more questions? Anything, burning things? Anything you'd like me just to quickly recap before we close this evening?
I do have another one again for a specific application. I'm trying to put my own internals into a retro bike light, and I've got a 3.7 volt LiPo rechargeable battery for it, and a 3-watt LED that runs at 3.3 volts. What would be a good way of dropping that voltage? Should I just put a diode chain in until it's low enough, or what?
Well, this comes back to what we was talking earlier. But that's quite a nice way for me to wrap up as well, can you believe? Before I plug our next event. Yeah, well, like we're saying there, John, if you put a diode in, yeah, you know, you can lose maybe 0.6, 0.7 of a volt per diode, but you're just dumping that energy as heat. And it's the same with the linear regulator. That energy's got to go somewhere, and it's converted to heat. So if you're drawing a lot of current, just to go back here.
Well, about an amp, yes.
Yeah, so just to go back to here with our circuit board. So yeah, I mean, you could have a small regulator, but of course it's going to get hot. You could put a big bruiser on, which is then obviously going to be able to manage the heat a lot better. But they're both terribly inefficient. So there's always a trade-off in everything. Switch mode, you know, would probably be more efficient, or buck boost regulator. So a buck boost regulator, if we didn't talk about, is another type of switch mode where the output will say stay at 3.3 volts. This is a buck boost, as it turns out. So if the voltage dropped to, say, you know, if you did put alkaline in and it dropped to say 1.5 volts, I'd still get 3.3 out. And if it was a good battery at say 5 volts, I'd also get 3.3 out. So a buck boost is a good solution. But as I said, if you're going to go down the clever route, the engineer's route, you need to design your switch mode such that its maximum current capability is what you want. So you don't want to have too much headroom, otherwise they start to lose their efficiency. So you know, they can be up at 94 at their peak, and then they'll start to drop off, you know, to maybe about 75 as you start to draw too little current from them. So they'll start then to heat up a little bit as you roll off the efficiency curve. And then you might not be any better than slapping a diode in, cheap and cheerful, which is sort of the sort of thing you might get, you know, some cheap rubbish off the market, might have a diode or a linear regulator. So yeah, you know, John, it's horses for courses, and I just say don't leave it till an afterthought. You know, it's the same with the balloon project. Just don't leave it as an afterthought.
Oh, absolutely not. The energy economy is the probably the most pressing question of the whole thing.
Yeah, well, it's the one as well that nobody pays any attention to. They just think, oh yeah, that'll be easy, and it turns out to be the undoing of the whole project.
It's one of the benefits of working in satellites. The energy economy is something you become a lot more acutely aware of.
Yeah. Well, my talking of satellites, I mean, my uncle was the chief engineer of Beagle 2 that landed on Mars in 2003.
Oh, cool.
Yeah, I mean, the stories around that mission are just astonishing. You know, you know, and what went on, and the fact it landed and unpacked, absolutely astonishing.
Yeah.
Well, look, it's been an hour, everybody. I'd love to talk longer, but we should try and keep to time. my plan is with these is I come up with an idea for about half a dozen to run on the first Wednesday of every month from about 7:30. And same sort of format. You know, next time I'll have a different board for us, which is actually in production at the moment because of Christmas. So we'll look at timers, and I've got some. Hopefully, I'll get an extra camera set up so we can look at the oscilloscope next time. So that's the 6th of January. And then after that, I thought we'd have a look at some logic and race hazards and Carno maps and op amps. And then designing for reliability, which is quite an important one because nobody wants it to fail. And then, yeah, we'll wrap up. So I think it's June, some dates. That's Wednesday of June. We'll wrap up with